Hi there, welcome back, and hopefully this will be our last video for this part 1 of the flexural members. And I plan to do two more problems, actually two different types of problems, or two different perspective of problems, actually different from the ones that we did in the previous video. So here it is. This one is taken from the textbook by Beer and Johnston, and this is problem 4.1. It says that the rectangular tube shown is extruded from aluminum alloy for which the yield strength is 40 ksi and the ultimate strength is 60 ksi. And recall that in the stress strain diagram for tensile test for steel, it looks something like this. And right here, this is the yield strength, and here is the ultimate tensile strength, denoted as sigma sub u. This one is sigma sub y. Okay, although this is for steel, it might be true, or it also exists. I mean, the yield strength and the ultimate strength also exist in some other materials, actually, some other ductile materials. So we have here sigma y 40 ksi, sigma u is 60 ksi, and E, the modulus of elasticity, is 10.6 times 10 to the 6 psi. Now, neglecting the effects of fillets, determine M, the moment for which the factor of safety is equal to 3, and for letter B, corresponding radius of a curvature. Okay, so what this means, if we neglect the effect of fillets, probably right here or right here, then that simplifies our problem, and we are asked to find for the internal moment for which the factor of safety is equal to, to 3. Okay, so for the solution, or here it is for the illustration. So we have this rectangular tube, and we have a 5 inches for this dimension, for this length, and we have 3.25 inches for this length, and we have a thickness of 0.25. Okay, so for the solution, we need the internal forces, right? We need the internal forces. I mean, typically, if we are asked to find for the stress, we need the internal forces and the geometric properties. But right here, we are asked to find for the internal force. So there must be a way in which we can obtain the value of the stress. Okay, so we have the stress. I mean, we can solve for the stress, and what we need is the moment of inertia, the geometric property. Okay, so solve first for the moment of inertia. Okay, so the moment of inertia of this section, this is a composite section. Right, so it's just equal to the rectangle, I mean to the outermost rectangle, and let's shade this one. So the moment of inertia of this one is just equal to this minus the inside rectangle, and the dimension, this one is already given. This is 3.25, and the length is 5 inches. And for this one, we just have to subtract the thickness, and this will be 2.75, and this length would be 4.5, right? So it's just 5 minus 0.25 minus 0.25, so it's just 4.5. Okay, so the I total is just simply I sub 1. Let's say this is 1 and this is 2. I sub 1 minus I sub 2. Okay, so I total is actually the centroid is just the same right here. So we can just simply use the centroid equation, which is, I mean, we don't need to use the parallel axis theorem because the centroid just passes through the same point, okay, whether in this shape or that shape. So we have 1 over 12 times the base 3.25 times the height of 5 inches cubed minus the moment of inertia of this. This is 1 over 12 times 2.725, that's the base, times the height of 4.5 cubed. And this one is equal to 33.85, okay, minus 20.88, and this one would be 12.97 inch to the fourth. Okay, now we have this moment of inertia. Then let's solve for the stress, bending stress, or actually that would be the design stress, okay, the design stress, or sometimes they call that allowable stress. So that means that will be our range of stress. Okay, so or working stress. Okay, so just take note of the terms. It's called as the design stress because that's what we are going to use in computing some parameters. That's I mean, in I think the precise term when you say design stress is if we are into determining the geometry, for example, then this will be the stress that we are going to use. Okay, or allowable, sometimes it is referred to as allowable stress because that's just the stress range that we are going to use. Sometimes it's also referred to as the working stress because that's what we are going to use, right? So it's just terms, but the idea is just the same. And to compute for this working stress or allowable stress, and let's just use allowable stress because that's what the book used. The computation is that it's the fact it's the ultimate strength. Sometimes it's used in terms of sometimes the criteria right here is the yield strength. This is it, the ultimate strength divided by the factor of safety. But that actually depends upon the failure criteria, because sometimes the ones used here is the yield stress. So instead of the 60, sometimes the ones used is 40. But the book uses this one, this ultimate stress, ultimate strength, because it's in the strength side, ultimate strength, and we are going to divide this by the factor of safety and compare the value right here to the yield stress, so that we can determine if it's in the elastic range. Okay, so let's do that. This is 60 divided by the factor of safety of this is 3. So our value right here is 20 ksi. Okay, so if we comparing sigma allowable to the yield, to the sigma yield, actually this is the yield strength. And sometimes or in the machine design course, we use the symbol S, so that's just to differentiate the stress from the strength. Okay, and the difference between the stress and the strength is just simply the one is the one, I mean, the strength refers to the capacity and the stress refers to the load side. So how much stress are you going to put in that material? So that's the stress. But the strength is the capacity of the material. How much load can it carry? Okay, so that's why sometimes you would see this in the machine design course. This is S, and in structures engineering, instead of S, it uses a capital letter F. Okay, but the idea is just the same. Okay, let's just maintain the sigma because that's what the book used. Okay, so sigma y Let's compare this, and 20 ksi is less than the value of sigma y, which is 40 ksi. And what that means is that since this is sigma allowable is less than the sigma y, what that means is that therefore we are in the elastic range. Okay, so if we are in the elastic range, then that means we can solve for we can use the Fletcher formula because it's derived for the elastic region. When we say elastic region, it's like this. So if this is the stress strain diagram in tension, and let's say this is the stress strain diagram of steel. Okay, so here's our yield, and here's our ultimate strength, yield strength, ultimate strength. So right here we have this linear region, so that's the elastic region. Okay, so that means that we can apply the formula because the formulas were derived for this region, so the elastic regions. And when we say elastic, it just simply means that the material goes back to its original shape once the load is removed. Okay, so that's the region. Or the, okay, so now since we have the allowable stress and we have the moment of inertia, then um, we can now solve for the moment using the Fletcher formula. Right, so the Fletcher formula is just recall that this is the bending stress, but of course the bending stress is the allowable stress because that's what we are going to use. That's the working stress, and this is mc all over I, mc all over I, and we have this, we have I, we have C, so we can solve for M. So M is just C, sorry, this must be allowable, sigma allowable, right? Sigma allowable times I divided by C. Okay, and if we continue here, M is equal to 20. Take note, this is 20 ksi, so that means kips per square inch. So let's convert this to psi. This is just 20,000 psi, and times the moment of inertia of 12.97. So 12.97 inch to the fourth divided by the distance from the centroid to the outermost fiber. That's and by the way, why do we choose the outermost fiber? That simply means that it's the biggest, or it's where the maximum stress is, and that relates to the maximum moment as well. Okay, so the distance from the centroid to the outermost fibers, if this is 5, then the half of 5 would be 2.5. Okay, so 2.5 inches. And this one would be 1,000 or 103,760 pound inch, or in terms of kip inch, this is 103.76 kip inch. Okay, now we're done with A, and let's solve for B. Now for letter B, okay, so solving now for the radius of curvature. And we can solve this using the moment curvature equation. This is just 1 over rho is equal to m all over EI. Okay, and if we substitute the value, we have 103.76 times 10 cube pound inch divided by E, which is 10.6 times 10 to the 6 psi. and the eye is 12.97 inch. I think this is inch to the fourth. Okay, and just take note, this is 1 over rho. So you have to, if you compute this, then you have to divide that by, I mean 1 divided by the answer. And what you get here is a rho of 1,325 inches, or in terms of feet is 110.4 feet. All right, now we'll do another sample problem, and this one is another type of problem. I mean, in terms of the computations, this one is different. Okay, this one is taken from the textbook by Philpott, and this is example 8.6. The problem says the beam shown will be constructed from a standard steel W shape, wide flange shape using an allowable bending stress of 30 ksi. We are asked to develop a list of acceptable shapes that could be used for this beam, include the most economical. So we are going to select from W8 or W10 or W12, W14, and W18. So we are going to make a list, and we are going to select the most economical W shape for this beam, because since this I beam is actually a high beam, that's the general term that, or typical term that we use for this type of shape. But the precise one, this is referred to as W shape, because there's another shape that's also I, because there's a lot actually. So we have this, if we draw here, let's say we have this W shape, and there's another one, the S shape, and it also looks like an I, but the difference is that we have a tapered portion right here at the flange. So here's the flange. This is referred as the flange. That's why this one is called as wide flange. Okay, and this one is a standard shape. And this portion right here, this is what we call the web. Okay, so we have W shapes, we have S shapes, and we also have um, something like a heavy version of this one. And I think this like HP. I don't know, I forgot it. All right, it's for bearing piles. Okay, so it's just something like a heavy version of these W shapes. Okay, so since these are standard shapes, then there's gonna be a list. If you recall from the, I mean, when we talk about the section modulus, the geometric properties, and I've shown to you the tables. So there's a list of sizes of these eye shapes, and we are just going to select which would be the most economical, because there's a lot of shapes that's possible for the design scenario, but in terms of economical, and when you say economical, this would be in terms of the material. So we should have a least material that could do the job. Okay, so here's our beam, and we have this loading situations. We have a distributed loads, we have concentrated loads, and we have concentrated moments. And the support is, this is a simply supported beam, since we have a pin and roller supports. Now I've just fast forwarded this, and I've just given you the moment diagram. And right here we have the maximum moment. You can see here we have a maximum moment of 70.83 keep foot. Okay, so that's gonna be our design moment or working moments. 70.83 keep foot. And by the way, this is a degree 2, because if this is linear, I mean constant like that, then the shear would be degree 1. So this will be degree 2, this will be curving degree 2, and this one also, and this one also. Okay, so Okay, so once you have the moment, then we can let's write it here. Solution. Um, let's apply the flexure formula, and our flexure formula is just sigma b is equal to mc all over I. But recall that this I and c, this can be expressed as the section modulus. S, recall that S is equal to I over C. So this one, this bending stress, can be written as M all over S. Okay, so for the stress, we'll be getting the value of the stress from this given value right here, and but this is the allowable bending stress. Okay, so here's our bending stress in terms of equations, or how we write it. The bending stress is equal to M all over S, but it says that we only have this or we have this limiting value. We have this allowable bending stress of 30 ksi. Okay, so this must be the value of this one must be less than the allowable. Okay, otherwise, if it exceeds the allowable, then that's going to fail. So if we consider these two terms, right, I mean these terms right here, then we can rewrite this as S is greater than, or S must be greater than equal to the M all over the allowable. Okay, so here's going to be our equation, that the section modulus that we computed must be greater than or equal to the moment divided by the allowable. So this one is equal to the moment is equal to 70.83, and this is keep foot, and we are going to convert this to inch. So this must be multiplied by 12 divided by 30 ksi, because this is the allowable. So take note, this is inch, so that's why we need to convert this to we need to convert the foot to inch. Okay, and this is in kips, and this is also already in kips, so that's fine. What we get here is a value of 28.33 inch cube. Okay, so here's our at least, or actually it must be greater than or equal to this value, 28.33. So we need to go to the table to select. Okay, so let's write here, go to the table to select shapes, appropriate shapes. Okay, so we need right here it says we need W8, W10. So we should write here W8, W10, W12, and W14, and also W18. Now going to the table, here's our table. At the back of the textbook, there's actually a wide flange sections, but in SI. But there's another one in US units, US customary units. Okay, so you would notice here we have a designation of the wide flange sections. We have 24, 21, 18. So it's from the largest to the smallest. So right here we have W6, and here is the W8. So we are going to select section. So which W8 section right here, because there's also a lot that's listed here. I think there's 5 that's listed here under W8. There's 5 in W10. In W12 there's much more. So we are going to select the section modulus, and that the section modulus that must be higher than 28.33. Okay, so here's the column for the section modulus, right? So I just mark it here. Okay, so let's start with W8. So from W8 by 15, the section modulus is 11.8. So that's less than. So we have to select a section that will give a section modulus that's greater from the ones that we computed, and the ones that we computed is 28. So right here our candidate would be this section, 8 by 40, right? So that's uh, our selection for W8. And for W10, uh, this will be 32.4. So our selection would be 10 by 30. And for W12, this will be 12 by 26. Okay, because this is greater than the section modulus. And for W14, we can have, I think we can select this one, the 29. And for W16, we have the lowest value here is um, 47.2. So we have 16.31. And of course, this is SX because right here, the axis of rotation is along this. So we are bending the shape along this axis. Okay, so let's write down our selection. For W8, we selected 8 by 40, and the S is equal to 35.5. And for 10, we selected a 10 by 30, and the section modulus is 32.4. And for W12, this is 12 by 26, and the S is 33.4. And for 14, we have 14 by 22, and the S is equal to 29. And for W18, I think this should be, okay, W18. So it's not 16, it should be W18. So we can select the 18 by 35. So this is 18 by 35, and the S is 57.6. So the most economical section would be, and let's write here. So the most economical section would be the lightest, section. Okay, when we say lightest section, that corresponds to the mass of the section. So in this designation, as I've said, the first digit right here, or actually the first digit right here, the W corresponds to the shape. So if it is S shape or if it is L shape, but right here this is W shape, and the second digit right here, this is 8, 10, 12, 14, 18. This corresponds to the depth of the section. So when I say depth, I think that's the nominal depth. So it's not really this depth right here, but something like a nominal depth, because if you check the table, there are there are it's not actually exactly equal because there's some root right here, root distance, and probably the flange distance. But anyway, that's the nominal depth, and the here, right here, this is in I think this is in pounds per foot. Okay, so that's the weight. That's the weight of the object or of the section. So that means that if you have a um, 40 pounds, so that's heavier as compared to the ones lower than this. So the lowest would be this one. Okay, so therefore we should select W14 by 22 by 22. Okay, so that's one application of this flexure formula and the section modulus. All right, so I think that's all for this part one of the flexural members. And in the next lecture, we will move on to the part two of the flexural members, in which we will discuss the shear force. Because recall that what we did or what we considered, because if this is the beam section, right? We know that there's moment and there's also shear. But for the moment, that's the flexural stress. That's the MC over I, and we haven't considered yet the shear force. So there's another. I mean, we'll discuss that in the next videos. And also, what if we have a composite sections? Like, for example, if we have a wood and a steel. So if we have a composite sections, then we'll also solve the flexural stresses with that. All right, so I think that's all. So see you in the next videos.